In this video, we're going to be taking a look at Dropout. In essence, Dropout consists of randomly selecting hidden units or neurons and setting all their outgoing edges to 0. This is useful in preventing overfitting. If you want to check out the actual theory behind it, you can go ahead and go to the following link. I'll put a description to it in the video. And so to start off, we're going to want to import the following libraries. And we're just going to be using the MNIST dataset because we should already be familiar with that one. And so we don't really have to focus on anything else. This should be a capital X. All right, so essentially the MNIST dataset consists of hand-drawn digits, and we're going to use a neural network to try and determine what number this is. And so, for example, this would be a 5. Before we do that, there's a bit of processing that we have to do beforehand. And so the first thing we're going to want to do is we're going to want to normalize the data. And so for grayscale images, the pixel intensity ranges from 0 to 255. And in normalizing the data, we change it so that it ranges from 0 to 1. And then the next thing we're going to want to do is use the toCategorical function in order to encode our labels. And so by default, the labels should range from 0 to 9, but the way neural networks work is they might interpret that differently. And so in using this function, basically we'll set it up so that if it's a 5, then there will only be one in the position corresponding to the 5, and then the rest will be 0. So before we feed it into the network, we're going to want to flatten the image. So it's 28 by 28 pixels, and so we'll change that into a one-dimensional array. Then we feed it through a layer with 128 neurons. We use a ReLU activation function, and then we want to make sure that our last layer has only 10 neurons, each corresponding to one of the hand-drawn digits. So you can see it right here. We're going to go ahead and compile that. So we use categorical cross entropy because we're trying to predict multiple classes. And we're going to set aside 10% of our data for validation. And as a quick reminder, if we have a batch size of 32, then that means that 32 samples or 32 hand-drawn digits will pass through our neural network before we compute the gradient. And we compute the gradient and take a step towards the solution for a total of 10 times because we specified 10 epochs here. So we'll go ahead and run that, and then I'm going to pause the video and then come back when this is done. And we're back. And so let's take a look to see how our model did. And as you can see, the training loss continues to descend throughout the 10 epochs. And then our validation loss plateaus around the 3rd epoch. And then if we look at the accuracy, you can see that the training accuracy increases all the way to close to 99% on the training set. And again, our validation accuracy appears to plateau around 97%. And if we used our model to classify the hand-drawn digits in the test set, it gets roughly 97% accuracy, which is very good. So now what we're going to do is we're going to do the same thing, but this time we're just going to add a dropout layer. And as a rule of thumb, you'll want to place the dropout layer after the activation function unless it's ReLU. And since we're using ReLU, we're going to go ahead and put that in front. In passing 0.5 to the dropout layer, essentially we're saying there's a 50% chance that the output for a given neuron will be forced to 0. So we'll go ahead and run this. The rest is the same. And so while this is training, I'm going to go ahead and pause the video and then come back when it's done. And we're back. And so let's take a look and see how our model did. And as you can see, unlike the previous model that didn't use Dropout, our validation loss continued to descend after the third epoch. And if we take a look at the accuracy, we can see that, again, the validation accuracy actually continued to increase after the third epoch. So if I go back here, it might be a bit more obvious. So we did lose a bit of training accuracy, but again, that's fine so long as our model generalizes well, because ultimately that's the goal, is to predict unforeseen values. And so if we take a look at the accuracy on the testing set, you can see that it's 97%, which is roughly the same as the other one. And that's to be expected because you shouldn't really expect to get more than 97%. Like, that's already high enough. And so thank you for watching. If you have any questions, let me know in the comments.